So hello guys, welcome back to Geeks for Geeks Practice channel. And today, as we know that we are again going to discuss a recently asked problem statement. And now and today, the problem statement which we are going to discuss is called merge to sorted linked list. It is a pretty much common problem statement or a classical question of a linked list when you start as a beginner in the linked list. This problem statement was recently asked in Amazon, and this problem statement is now and then asked in every top product-based companies, in every top tech giant companies if they want to test your knowledge on the basis of linked list, right? So let us now study the problem statement of the given problem, right? So basically, we are given two sorted linked lists consisting of n and m nodes respectively. So what does that mean? This means that we are given two linked lists, right? And the size of each of the linked lists respectively is n and m. And our task is to merge both of the linked lists in place and return head of the merge list. So that means that at the end of the day, what our task is to merge or combine both of these linked lists in such a manner that the combined or the merge or the final linked list we return is always in the sorted order, that is in the ascending order, right? And one more constant put up to us is here is that we have to do it in place. In place means that we cannot use any additional extra space, right? So again, I'll summarize the problem statement. So basically, initially we are given two sorted linked lists of size n and m, and our task is to merge or combine both of these linked lists in place. That means without using any extra space, and we have to return the head of the merge list. So when I say that yeah, I have to return the head of the merge list, that means because in the linked list, if I want to traverse the linked list, right? So basically, if I want to traverse the linked list from the starting, right? So I should have a head pointer to start from the or to start iterating from the iterate all the nodes in that linked list, right? So let us now come to the problems, the sample test case to understand what we have to do at the end of the day, right? So I said that we are given two sorted linked lists of size n and m, right? So the first linked list has size of 4 and second linked list has size m is equal to 3, right? So all the nodes in the first linked list are 5, 10, 15, and 40. One thing to note here is that the linked lists are sorted, right? So all these values of the nodes are in sorted order. Similarly, for the second linked list also, the nodes have values in the sorted order, that is 2, 3, and 20. Now as we said that we have to return, or our task is to merge both of these linked lists, right? So and return the head of the merge list. So our output will be like this because we are merging both of these linked lists in the sorted order, right? Let us see how it is going on, right? So the our task is finally is to return the our task is finally to return our okay. Let me see why my screen is not visible. Okay, I hope my screen is visible now. Can you please let me know if my screen is visible? Can you please acknowledge whether my screen is visible or not now? Because there might be some issues. Okay, thank you. So let us now begin again with the problem statement. I hope much of the part is not missed. So this is the problem statement. The name of the problem statement, as we discussed earlier, is merge two sorted linked lists. So the problem statement is that we are given two sorted linked lists consisting of n and m nodes respectively, right? So our task is to merge both of these lists in place and return head of the merge list. So the problem statement says that initially we are given two linked lists and both of these linked lists are in sorted order. That means the word sorted means that the data in the nodes of the linked list are in the sorted order. And at the end of the day, our task is to merge both of these lists, right? So if we are given two linked lists of size n and m, then we have to return a single linked list combining of the nodes of the first and the second list in a sorted order, that is in the ascending order. And we have to do it in place. In place means we cannot use any additional extra space, right? So and we have to finally return the head of the merge list. So what does this statement means of returning head of the merge list? It means that if we are dealing with a linked list and we have to finally print out the linked list, suppose if this is my linked list and I have to print this linked list. So to iterate over all the nodes of the linked list, I have to have some pointer pointing to the initial node, right? So with the help of that initial pointer called as the head pointer, I can iterate over all the nodes, right? So this is why it is saying that we have to return the head of the merge list. Let us now see that sample test case to understand what is our task. So as said that we are given two linked lists of size n and m. Here, in the first test case, the size of the first linked list is 4, and the size of the second linked list is 3, right? And the value of the first linked list are in the sorted order, in the ascending order, that is 5, 10, 15, and 40. So we can observe that all these values in the nodes are in the ascending order. Similarly, for the second linked list, it is having three nodes, that is m is equal to 3, and the values of all these three nodes are in ascending order, that is 2, 3, and 20. So our output is, as we can see that our output is a single linked list consisting of all the nodes, that is n plus m nodes. So if we count all these values, all these number of nodes, these are n plus m nodes, and all these are in ascending order. So this is our task at the end of the day, that we have to return. So what is our task? That return a single linked list in ascending order, right? So this is what we have to do, and we have to do it. I'll repeat that we have to do it in place, right? So this is the main crux of the problem that makes this problem statement very interesting. That we have to do it in place, right? So let us now see that how we can relate this problem of a linked list into some other problem, right? So what if I say that if this problem statement was not of a linked list, right? So just forget for a moment that this problem is not of a linked list, right? So what if I say that we were given two arrays of size n and m, right? And these values were, let us say, 5, 10, 15, 40. We are considering arrays to understand more effectively this problem statement, how we can do that, right? 5, 10, 15, and 40, right? And in the second, the values are 2, 3, and 20, right? 2, 3, and 20. So if this would have been an array, how would we have solved it, right? So what we could have done, that we could have used two pointers, right? We could have two pointers pointing at initial of both of the array, right? That is pointing at the zeroth index of both of these arrays n and m, right? And after that, we will we would have been compared we would have been comparing both of these values, and we would have been using an extra space of size n plus m to storing all these values, right? So if I say that this size is n plus m, and I'll be start comparing values, right? So 2 is smaller than 5 because we have to run in the ascending order. That's why we are putting the value which is having lesser value first, right? We are giving priority to that value which is having a lesser value because we have to return in the ascending order. This point is made. So 2 is less than 5, I'll put 2 here. I'll move my pointer again here. 3 is less than 5, 3 will again come here. I'll move this pointer here again. I hope this approach is pretty much clear to you, and it is a very common approach of using two pointers to sort two arrays, right? The main task is to do this same thing in the question of a linked list, right? So 20 will come here now. 5 is less than 20, so 5 will come here. Similarly, 5 now again pointer will move here in the first array. Similarly, this will go on, right? So we would have been doing this if this was the case of an array, right? But we can see that in array also, we would have been consuming big O of n plus m space, right? Because arrays are static memory allocation. But in linked list, we know that in linked list, there is dynamic memory allocation. That means we don't have to specify or tell the compiler or tell the C++ compiler that yeah, or the CPU that yeah, we need this amount of space. If we want to add some node or some other space, we can dynamically allocate that, right, by using the new keyword. So this is why the problem statement becomes different in the case of arrays and linked lists, right? So with this benefit of us that we can use dynamic, because these linked lists are in dynamic allocation, we can do this without consuming any extra space of big O of n plus m, right? So this is what we have to do. I have told you the comparisons between arrays and linked lists so that you can gel up with both of these topics, that and what's the difference between arrays and linked lists, right? So let us now come back again to the linked list point. So in the previous videos also, we discussed that linked lists basically have one of the most important thing on which linked list works, or the life of the linked list, is the next pointers. The life and the soul of this linked list data structure is the next pointer. With the help of this next pointer, we can turn around the world of linked list. We can we can change the linked list as the way we want. That's why we will use next pointer here also to merge the linked list, the two linked lists in the and return the final linked list in the sorted or ascending order. Let us now look how we can do that. Before moving on to the big O of one space solution, let us now tell me the approach I used above in the case of array, right? So what we could have been doing is that we will be initially given the two pointers, that is head one of the linked list of the list one. Let me say that the first linked list is list one and the second linked list is list two, and we would be given two head pointers, right? That is head one and head two. We're pointing respectively to the first node of the list one and first node of the list two, right? So now what we could have done, that we would have been following the same approach as the arrays, but we can see that we use an extra auxiliary space because in case of arrays it is a static memory allocation. Therefore we have to initially specify the amount of space we will be taking to store the values, right? So therefore we know that if they are merging two linked or two arrays of size n and m, then the final array will be obviously of guaranteed size of n plus m, right? Because the total number of elements will be n plus m. It is obvious, no more than that and no more and no less than that, right? So now what we can do here, yeah. So in case of linked list also, suppose if I say that these are my two linked lists, right? Let me depict the values, that is 5, 10, 15, and 40, right? And thus this is my list 1 and this is my list 2, right? So in list 2 the values were 2, 3, and 20, right? So what we could have done in the linked list, if you know the basics of the linked list, that what we could have done, we would have followed the same approach, but with a little bit of twist, right? So the first pointer will be pointing to list 1 and the second pointer will be pointing to list 2, right? We will automatically follow the same approach as we followed in the arrays, and you will see here how. So I'll compare the first values, that is 2 is less than 5, right? So I'll create a new node. I'll put value 2 in here, right? This is my first approach in which I'll be using n plus m space, right? This is I am doing only to depict you that how we can follow the same approach of array with the help of a linked list, right? It is pretty much, this approach is pretty much easy to understand, or to begin with this question, that how it will be moving step by step, and how we will be iterating and doing step by step to come to our final answer, right? All the computations and all. So now I'll move my this pointer next here, right? So 3 will be pointing here, right? So 3 is now less than 5. I'll again create a node because as we discussed earlier, I'll repeat again for you that it is a linked list data structure, is a dynamic memory allocation. So we can create or allocate a space as and when we want. So therefore, I need a space here to allocate node with value 3 here. So I'll create a node by using new keyword and I'll put value 3 here. Now again, I'll move my pointer to 20, and therefore 5 is in 20 now. So again I'll need a node, and this step will further continue till both of these linked lists run out of their nodes. That is, both of them point to null, because null is the last address which depicts that we have ran out of the total number of nodes in each of the linked lists, right? So now this is how I'll be do it, right? So let us now jump onto the logic, how it is working on, right? So the logic says that, let me again draw the linked list for you. So what does the logic say? That both of these arrays or the linked lists are sorted, right? Sorted in ascending order. So if I point one my pointer here and another pointer here, P1, let us say pointer 1 and P2 pointer 2. So I have to return it in the ascending order, right? The final single linked list will be in the ascending order. So I'll be comparing these values, right? So if 2 is less than 5, then yeah, I can put 2 here, and I know that this I'm done with 2. Now I can again find another value in this second list having value less than 5. So in the quest of that, I'll move my P2 pointer to 3, right? And now again I'll see that whether 3 is less than 5 or not. Yeah, 3 is less than 5, so I'll again put 3 here and I'll move my pointer again here. Now in this case, I'll see that my P1 pointer, element at P1 pointer 5 is less than 20. So I will put 5 here and I'll move 10 here. 5, my P1 pointer to 10 here, right? This is how we are doing because we are using the benefit, or we are using the fact that both of these arrays or linked lists are in sorted order, right? So we can move my each of the pointer one by one according to the condition that whether which of my current list's element is smaller than the other list element, right? So this is how we will do, and this is how it will go on. So 10 will come here, then 15 will come here, then 20 will come here, and at the end 40 will come here. This is our final answer, right? So we can cross check our answer. So yeah, so this was our answer: 2, 3, 5, 10, 15, 20, 40, right? So it was 2, 3, 5, 10, 15, 20, 40. So yeah, we are doing great here till now. So yeah, so I discussed I discussed with you the first approach, right? First approach with the linked list, and it was consuming big O of n plus m space, right? So if I'm doing in the same manner as an array, as of array, so what's the benefit of doing this question in the linked list, right? If we know that linked list is in dynamic memory allocation, so I can use that fact, right, to improve our space complexity to something better than big O of n plus 1 m, because in linked list we have a next pointer, so I can arrange and move my next pointer as and when I want to manipulate my linked list, right? So what I'll do now, yeah. So let us now see how the things will go if I want to do something better with the next pointer and do something better than O of n plus m space, right? So if my linked list was this 5, 10, 15, and 40, right? And another linked list was 2, 3, and 20, right? So yeah, this was my list one, and this is my list two, right? So initially we know that we have to return a final linked list, right? A final linked list will look something like this, right? So we know that we have to return a head pointer such that when I return my final answer, the third person who is expecting the answer, he can traverse the linked list, or he can traverse the final linked list and check the output, right? So I have to return a head pointer for traversal of the complete linked list, because there is no other way of traversing a linked list other than having a head pointer pointed to the first node of that linked list, right? It sounds pretty much logical. So how we'll do that? How we'll move on with that? So first of all, as I said that we first of all in the linked list, the first main step is to have a head node, right? So we will determine the head node first of all. So how we can do that? Because this is our base case, so we will do it in the brute force manner, right? So we first of all have two pointers pointing to the head one and head two, right? So yeah, so we will compare both of these values of head one and head two node. That is, I'll see whether whether uh, which of the element of list one and list two is smaller. The element which is smaller, I'll I'll point on that node with my final answer head, right? So if head two is smaller than head one, I'll put the value of head two in head, right? Because at the end of the day, linked list is all about the game of addresses, right? Head one is pointing to an address. Head two is also pointing to an address, right? So I have created a node which is having an address, right? So if I do head is equal to head two, that what does that mean? That means that I am storing, or I am pointing the address of head two with the head, right? So my head two, now I can access my head two with head also, because it's all about address, right? If I have the address, I can access the value at that address too. So that's why if I point the address of head two to head, then I can access the value at head two with value head, right? And at the end of the day, I have to return head only, right? The initial head point of the final node. So our first task is done, that we have initialized our head node of the final linked list we have to return, right? So now how I will move on again with the next step, right? So again, I'll draw for more clarifications, right? So that you don't get confused the topics or the sub parts that I'm trying to explain. Because I'm trying to explain part by part so that you don't get confused and you get and so that you get to understand each part bit by bit and you can final on merge on all these parts so that we can get to the final answer, right? This is how I love to approach the questions. That is, for the final increases 2, 3, and 20, right? So we have determined the head node. So in this case, the final head node will be 2, right? And now I'll move my P2 pointer here, right? So my head 2 will now point to here. Let us create some more space. Right, so my head 2 is pointing here and my head 1 is pointing here, right? And this is my head node of the final linked list I have to return. So it is storing value 2, right? Now, it's storing value 2 means that head 2, the address of the head 2 is now stored in, is now can be depicted by head, right? Because we have pointed the address of head 2 in head, right? So I can access the value at head 2 or or the next pointer at head 2 or all the attributes of head 2 at the initial phase with head now because I have stored the address of head 2 in head. And in linked list, everything the game is all about at the end of the day is all about the addresses, right? So yeah, after saying that, now we will move on to the next steps, right? Now, instead of creating a new node as we did in the previous approach, we will move the next pointers of both of this linked list to join this head node. So I hope you're getting that what I'm trying to do is that instead of creating a new space or allocating a new space for a new node, I'll be moving or shifting the next pointer of these nodes to join the head node, right? I only have created a single head node, right? Instead of creating all the n plus m nodes, I'll be basically creating a single node because it is necessary to have a head pointer, right? So for that base case, I have created a single node. Instead of creating all n plus m nodes, I just created a single one node, right? For the sake of the head pointer. So now after that, this is now my head, right? And my next pointer of my head is empty. So now I'm waiting whether at which node my this head's next pointer will point to. So head 2 is now pointing here, right? So I see that, yeah, 3 is less than 5. So I'll point my next pointer of this head node to here, right? So instead of creating a new node, I'm shifting my next pointers to the initially given linked list to us, right? This is how it will work. So now, right? So after this, my head 2 will point here. So basically, if you see that the pointers approach, the two pointers approach is working in the same manner as it was in the first approach and it was in the approach of the arrays. But the main thing we are using here is that apart from the two pointer approach, because there is no difference or no changes in the two pointer approach, we are only utilizing the next pointers, right? So now this was my 2. I use the next pointer to point to the node having value 3 of the list 2, right? And now I haven't created any extra space. You can see that I haven't created any new node, right? I just shifted the next point of this initial head node to the 3, the node with value 3, right? And now I have moved my head pointer to 20. Now I will see that whether my 5, the node at head 1 and the node at head 2, I'll compare both of these values again, right? So 5 is less than 20. So what I'll do is then I'll point the next pointer of 3 to 5 here, right? Instead of creating a new node again, I'll be pointing my next pointer of 3 to this, right? And I'll move my head pointer here. So now my head pointer will shift to 10, right? Head 1 pointer. I'll again compare my 10 with 20, right? So 10 is less than 20. So I will leave this head pointer as it is, right? So 5 will now point to 10. And again, I'll move my head 1 pointer to here. So my head 1 will point here now in this case, right? Again, 50 is less than 20, right? So if you can observe that I am bolding or I'm marking bold all the next pointers so that you can see that what the route I was following, right? So what is the path of the linked list, right? So We started from 2. I changed the next pointer of 2 to 3. And from 3, I changed the next pointer from list 2. I changed my next pointer to list 1, right? Because I have the head pointer. So I can do anything I want to do. I can do or shift next pointers to anywhere I wish to point out, right? So from list 2, I changed from the list 2, I changed the head pointer of this node or the next pointer of this node to list 1, right? And from 5 I reached to 10, and then from 15, right? So now my head 1 is pointing to 40, right? Now I compare my value at head 1 node is 40 and head 2 node is 20, right? So 20 is less than 40, right? So basically my 15 pointer will now point to this node, right? So I am shifting, so you can pretty much feel that I am just shifting my next pointers instead of creating a new node every time, right? So I'm utilizing my space and I'm saving my space in this manner using the next pointers, right? So now now this 20, this list is now empty, right? So I'm left with the only node 40. So I'll just traverse the remaining nodes of each of the list, and I'll just simply add this node, right? So after 20, I'll add a 40, right? So this was my final route I was following. It is from 2, I was pointing to 3, and I pointed to 5, then 10, then 15, then again I came to 20, then I reached to 40, right? So if I draw it more clearly for you, 5, 10, 15, 40, it was my list 1, and my list 2 was 2, 3, 20. So one more thing I would like to tell you that in every question or in any question of linked list, you can get the crux or you can understand how things are going internally only when you draw the linked list, you see how the next pointers are working, and you see each and every iteration. That's the only way you can imagine and visualize the linked list working, right? So without visualizing how the linked list work, you won't be able to solve any single question of linked list, and trust me on my words, right? So this is the main trick or the hint or the hint of the day, you can say that, how to solve the linked list questions, right? So basically, if you face any linked list questions, you initially draw the linked list. You just initially change the next pointer, see how the next pointer will do computations to issue the final answer, right? So this is the only approach of solving linked list questions, right? To visualize and then to do the coding part of that. So yeah, so initially my head was my final linked list head pointer was here. Then I moved to 3. Then from 3 I shifted my next pointer to 5, right? And from 5 I moved on to 10. You can observe that I'm shifting only next pointers, right? I'm repeating that because I'm not utilizing any extra space. I'm just shifting my next pointers, right? From 10 I moved to 15, shifted my next pointer of 10 to 15, and the next pointer of 15th node with value 15, I shifted that next pointer to 20, right? And from 20 onwards, I shifted my next pointer of 20 to the node with value 40. So basically, I'm just using next pointer to point to the next address of each and every node, right? So linked list is all about addresses, right? So if I write it down, then I'll do no wrong that linked list is equal to addresses and managing those addresses with the help of next pointers. That's all. This is all the crux of the each and every question of linked list, right? So you can consider it as a cheat or cheat sheet or anything like that you want to call, but this is how we do the linked list, right? So I hope it is clear that how we are using the next pointers and so on. So let us now discuss the time complexity of that. So we can see that we are traversing both all the nodes of both of the list, right? So time complexity becomes big O of n plus m because we are traversing each and every node of the list, that is n nodes plus m nodes, right? This is my time complexity, right? And if I talk about the space complexity, this was the main crux, right? This was we came to an efficient solution because I wanted to improve my space complexity, right? Space complexity is big O of 1 because I'm not using any extra space. I'm not creating any extra space using dynamic allocation. I'm just shifting my next pointers of each and every node of of both the list one and list two according to the conditions. The condition that whether which of the node is less than the other node, right? And according to that condition, I'm shifting my next pointers, and that's all. That's how the game ends, right? So let us now move on to the coding part. Let us how see how we will do the approach we discussed. I hope this approach and all the approaches I discussed. I started from the array, then I performed an analogy that what is the difference between array and linked list. If I do the same question on arrays and if I do the same question on linked list, so what's the difference between that? The difference was that in arrays, it is in the case of array is a static memory allocation. So we have to specify at the beginning of the task that yeah, I need this much amount of space, right? But in case of linked list, the only benefit of linked list is that we can use the dynamic memory allocation and allocate as much space as we want as and when we need it, right? So this is how it was all, right? So let me just revise it for you. So if any new viewers has just joined it, so you can understand also, right? So our question was to merge two sorted linked lists in place order, that is using big O of one space only. So I just started off with the question with the analogy of an array. If this question was given us to in the form of array, then how would we have solved it, right? So the only way to solve this question in case of arrays was to use big O of n plus m space because it is static memory allocation. But in case of linked list, we could have done this with the big O of n plus m space, but it was a very naive approach because we are creating at each and every iteration of the both of these all the nodes of the linked list, we are creating another space or another node, right? So it will pretty much obviously occupy big O of n plus m space, but we can do it better pretty smartly and wisely by using the next pointers, and the life of the or the soul of the linked list is only the next pointer only. So you can mark my words on this, and then after we discuss the approach, I discuss all the step-by-step iterations, what we'll do. And I gave you a sort of cheat sheet that what is linked list. Linked list is basically managing the address using the next pointers. That's all, right? So if any question of linked list comes to you in any of the interview, what you should do that, pick up a pen, paper, just draw the linked list and use your brain and see how the next pointers will do iterations in the linked list so that you can reach the final answer, right? So yeah, let us now move on to the coding part. So yeah, this is our practice portal of Geeks for Geeks, where you can find a hell lot of number of problems on according to the company tags you want to apply the tags, or on the difficulty level on the topic tags or the company tags you want to solve on. That's up to you, right? So before starting this coding part, right? So you can cross check the questions. The constraints are n and m will be less than equal to 10 raised to the power 4, right? So we have the expected time complexity was big O of n plus m, that is size of both of this sum or summation of the size of the both of these linked lists, and the auxiliary space was big O of 1, right? So before starting the coding part, let me tell you the structure of the node, right? So basically in linked list, we define a structure of a node that what will be the attributes or what will be the entity of each and every node, right? So in a single node of a linked list, we'll have a data value, we'll have a data part and a next part. The data value will store the data or the value of that particular node. That is the information that node will be storing. And the next pointer will be used to point to the next node of that particular linked list, right? So this is the constructor part of thing, because if you use a new node, then and if you pass a value, so with this, it will automatically create or insert the value that you passed for the new node into data, and it will allocate the next pointer to the null, right? So this was all about the approaches and how the we will working with the algorithm, right? And now we will move on to the coding part. So yeah, so we will simply code down the big O one space solution, right? So I'll code down the big O of one space solution, right? So one more thing, interesting thing is that I'll just not write down the code, right? I'll just move on to the writing pad part, and I'll explain that what like how does the code is visualizing it, right? I'll make you imagine what the code does, right? So that you can understand what each and every line of the code says. what each and every line of the code is trying to say, that what, yeah, I'm doing this specific task, right? So it will be much more easier to visualize and imagine and how this code is working, right? So as we said that, first of all, there will be some base conditions, right? The base condition will be that if it might be possible that both of my linked lists are empty, right? So in that case, if both of my linked list is empty, then what we have to do? We have to just normally return a null. Null means there is no node we are having in the final answer, because both of these initial linked lists which we were given were empty, right? So I'll say that if my head one is equal to null, and if my head two is also null, that means the size of linked list is 0, or we can say that no nodes in any of the linked list, right? So I hope you understand the commented part. I'll comment it down at each and every step so that you can understand what I'm doing at each and every step, right? So this is the case. I'm covering all the base cases because we can miss the base cases in the case of linked list, right? So we can get a segmentation fault error, and it is pretty much common error we face if we miss any cases or the base cases in the linked list, that it is obvious that we'll get a segmentation fault. So we have to take care of the segmentation fault in the questions of linked list, right? So if my, so this is the first case when both of this list linked list will not have any nodes, right? So I have to return normally null. That is, in the final answer, also there will be no nodes, right? Now, the second case is that if any one of the node is empty, right? If any one of the linked list is empty, that means only one of the linked list is having nodes, right? So how we can write that? If my head one is equal to null, that means I'll normally return head two, right? Because if my one of the linked list is empty, so what I'll basically do? If my one of the linked list is empty, that means I have only one linked list, right? So we can deduce from that, if one of my linked list is empty, then I have only one linked list left. So I will basically return that remaining linked list, right? Similarly, for the case of if my another linked list is empty, I simply return the remaining linked list, right? So this is my another base case. If any of the linked list is empty, right? This was my first case. This was my second case, right? And now after doing this, we have covered all the base cases. Now what we'll do that I'll create a first head node, which is necessary because I have to return the final linked list with the help of the head node, right? So what I'll do is I'll create a head node, right? I'll by doing this, creating a head node for the final linked list, right? Yeah. So now I have allocated this space for only single linked list, right? So I can write it down that too. Allocating the space for only the head node of the final answer, right? Now after that, as we said that we first of all have to look at which node will be the first head node of the final answer, right? So for that, I have head one pointing to the first node of the list one, and head two for the second node, for head two for the first node of the list two, right? So I'll be comparing both of these values, right? And which of the node value is lesser, I'll put that into the head node, right? So that the same I'll do here, right? So what I'll do for that is, if head one data is less than head two data, then what I'll do? I'll I'll point the, or I'll store the address, or I'll point the address of head one into head. And now this is done. So I have to move one step further in that particular list, right? So what I'll do is head one is equal to head one's next, right? And similarly, head is equal to head next. This is because if I've allocated an address to the head, right? So I have to put on another node, right? So for that, I have to move on to the next pointer of the head, right? So what I'm trying to say is that if I'm pointing here, right? So currently, by allocating this particular the smaller of the values of the head 1 and head 2, I have allocated the two head, right? So what should I do if I have to allocate another value, right? So I'll if this is my head, I'll move on head is equal to head next, right? So I'll point somewhere here, right? I'll be standing at somewhere here, and when I do the second iteration or second comparison, then I'll be allocating that node's address to the next, right? I hope you are visualizing what I'm trying to say. So this is done, right? And second case will be if my, or I can simply do else head equal to head 2. That means that if head 1, head 2's data is less than head 1, then okay, then I will move in the next, I'll move to the next node of the second linked list, and I'll again move in the next point of the final node's head node, right? Yeah, this is how we are allocating the first node of the final linked list, right? And now allocating the remaining nodes in the final answer, right? So in this part, we'll be allocating the final, all the remaining nodes in the final answer. So for that, what I'll do, I'll traverse till any of the linked list becomes empty, right? So what does that mean? If I'm having two linked lists, right? Say these are the both linked lists, right? So if any of the linked list reaches out the number of nodes, then I just normally have to put the remaining nodes of any of the linked list in the final answer, right? So that means for that, if what I have to do or at the condition to consider that, yeah, one of my linked lists have been run out of that number of nodes, total number of nodes in that particular list. For that, I've written down while head 1 and head 2. That means while head 1 is having number of nodes, while and head 2 is having nodes, right? Or we can say in other words that while head 1 doesn't point out to null and head 2 also doesn't point out to null. If any of them point out to null, that means any of the linked list has been ran out of the nodes, and when this loop ends, I'll just put all the nodes of the remaining linked list into the final answer. So yeah, what I'll do is that now I'll again do comparisons. If head 1's next, head 1's data is less than head 2 data, then I will point the head 1 to head, right? Because head 1 only means the address of that particular node. So and head also means the address. So I'll point the, because head is pointing to the next node, right? So head, now my current head pointer is just waiting to be pointing to the next node, right? So it is basically in the wait condition, and it is waiting for the next node where it should point, right? So it should point to head 1 if the data of head 1 is less than head 2, else it should point to head 2, right? So in this case, head will point to head 1 if, right, if this condition is satisfied, and I'll move a head 1 pointer to the next node of the list 1, right? Else I'll do is that my head will point to the head 2, and similarly same logic goes here also, that I will move I'll move in the second node of the list, right? So as I said, as we discussed earlier, that once we are done with the pointing the current node which is having a lesser value by doing the comparisons here, now I have to move, or I have to move to a new state in the final answer such that I can allocate a new address to that node, right? So for that, I'll be doing head is equal to head next. So I'll repeat that. What I'm doing here, basically, suppose if if I have reached here, right? If I reached here, then I'm currently, by doing head is equal to head next, I am currently waiting at this next pointer, right? I'm waiting for the next node to be put in the final answer. So that's why I have done head is equal to head next. And whenever in the next iteration I get a smaller node value, I'll attach that next pointer to that node, right? So this is what I'm doing here. So after this loop will get over, it is ensured that only any one of the linked list will be exhausted. That means will be completed, right? And now we have to add the all the remaining nodes of that. We have to add all the remaining nodes of that linked list which is having in the final answer, right? So how we can do that? So basically, what we'll do that suppose uh, if 40 is remaining, or suppose if 15 and 40 are remaining, right? And this linked list has been, suppose there is a case that only 2 is the value and 15 and 15 and 40 are remaining. So what I can do, I can simply put the 2's next pointer here, right? Instead of traversing each linked list step by step, what I'll do is that I'll just simply put the next pointer of 2 here, because 15 and 40 are always in ascending order, right? So there is no need of traversing again them. I will just simply put the next pointer of 2 to 15, because after putting the next pointer of 2 here, 15 and 40 are already in ascending order. So no need to do computations on them, because they are already in sorted order. And if I attach the remaining part of the linked list in the final answer, the final answer will always remain in sorted order, right? So that's all I do, that if my head one is not. So what this condition means, that if head one is empty, right? If head one is empty, or empty means head one or the list one has reached or ran out of the number of nodes. So if head one is null, if list one is empty, that means head one will point to null. But I have put the not here. That means null will be negated to true, and that means I can point my head 2, right? Because if head 1 is null, list 1 is empty, so the only list remaining will be list 2. So I'll putting the next point of the final answer node, and shift the next pointer of that node to the list 2's remaining node pointer, right? And else, if head 2 is empty, then I will put head 2 head 1, right? And at the end I will return head. So now I just want to teach you one thing, that what do you think, whether this will be done or not? The answer will be no. This is because we have written a head pointer, and if you observe it carefully, we were iterating the head pointer, and we are moving head pointer one by one step by step till we reach the final node, right? So when all these iterations will be done, our head will be pointing to the last node of the final answer. So if we return head here, it will return only single node. That single node will be the last node of that final answer, right? So for that, let us let me make you imagine again, right? So what I'm trying to say, that my head pointer was 2, and I was doing head is equal to head next every time, right? So now no, if I do head is equal to head next, my head will be pointing of the final answers head node will be pointing here, right? And again, if I do head is equal to head next, as I was doing in the coding part, that is here head is equal to head next every time. So my linked list, my final linked list head pointer will now point to 5, 10, 15, 20, and 40. So if I return head at the end of the day, then they will be returning only single node, that is 40, because head is now pointing to 40. So for that, what I'll do is that I'll keep a temporary pointer, right? I'll keep a temporary pointer. I'll point it to head. So what does that mean? That means, so here I'm allocating the pointing the head node of the original list to the temp pointer, right? So what I'm why I'm doing this, because I'm doing the traversals or the iteration in the final list with the help of head pointer, right? But I have to turn the head. So as I told you that linked list is all about manipulating addresses, right? So I just basically stored the first node's address in the temporary. So if I return the temp, then what does it means that I'm returning the head of that linked list, because I have stored in the before doing all the iterations in the final linked list, I have stored the address of the first head node of the final linked list in the temp. So if I return temp, I'm basically returning the head node of the final answer. So let us see again what I was doing. Let us overview the code. First, I just take care of all the base condition. That is, if both of the linked lists don't have any of the node, that is size of both of the linked lists is 0, right? And after that, I check whether any of the linked list is empty or not. If any one of them is empty, then I'll simply returning the only linked list I'm left with, right? And after that, I created a head node, right? And I just pointed the first node, which is smaller in value, to the head node. After that, I just added on the remaining nodes of the both of these linked lists to the final linked list head, right? And after that, if any of the linked list is being ended, and I'm left with any one of the linked list, let it be list one or list two, I'll be adding all of these nodes in the final answer, right? Let us now see. So yeah, this is giving error. This is returning me only 3 and 20, right? So there might be some error. I just head is equal to head one. This is right. This is right. Head one's data is in head two's data. Head is equal to head one. Head one is equal to head one's next. Right. So it is showing me an error. Let's see what's the bug here. Hmm, I hope everything was okay. Hmm, Let's review our code from beginning. Right. I had node one. If head one is equal to null and head two is equal to null, allow me to return one. If my head one is null, I return head two. If my head two is null, I return head one. There's no issue in that. And after that, if my head one's data is less than head two's data, mm, I'll point on. Okay, if head is equal to head one, there's no issue in that. If head is equal to else, I have put head is equal to head two is head two next, and okay, there seems no issue in that too. Okay, there's no issue in that. This one, let us start again. Okay, I have node head or temp. If head one data is less than head two data, null point head is equal to head one. and my head one will point to head one's next, right? Okay. Okay. So one thing we messed up here is that we don't need this condition, and similarly here, don't need this condition also, right? And what I'll do is that this point here, head next is equal to head one, right? And similarly here, yeah. So I guess that's all. That was the error, and I guess it should work now. So basically, the error which we were encountering. Let me refresh it. So basically, the error which we were encountering here was uh, that we were just shifting too early the next point of the head node, right? So basically, yeah. So if I did after allocating the first nodes, first node like if after allocating the first node and the first node of the final linked list, if I do the head next here, then I'll be pointing to the null, right? So basically, instead of doing that, if I have allocated a head, right? So 2 is my here. So instead of moving to the next node, what I'll do, I'll just point the if I'm currently standing at head here, right? So I'll point my next data of this node to the head one, right? Like this, right? So this was the common mistake which we had committed here. So yeah, that was the error which I was talking about, that we can do some silly mistakes due to which segmentation faults and errors like that may come. So let us now try to compile that. So yeah, it is now working pretty much well here. Let's now try to submit. Okay. So now my last node is not getting inserted, right? So okay. So here also I just did some silly mistakes that head next will be here also, and yeah. So because after that, when this loop will be over, right? So if I'm pointing head to the head next, right? And this node is my over. Like if any one of the linked list is my over, right? So what I'll do is that I'll point my heads next to that remaining linked list, right? So if I had not done heads next here, so the last node or the remaining part of the linked list which will be remaining will not be added here, right? So these were all the silly mistakes I committed here while coding part, right? So this was all about, I was talking about that these are the silly mistakes we can commit, some hurry and all. Let us now try to submit that. So it is getting accepted. So if I explain my approach here again, that first of all I'll point my head node to the first node, right, using the base condition. After that, I'll shift my next point of that node to the node which is next smaller node among all of these list one and list two nodes, right? After that, my head next will point here, right? So basically, what's happening here is that if I depict you again the mistake I was committing here, because it's necessary to understand the mistake we are committing, right? So what I was doing basically was that if I'm pointing to here, right? So I was doing, and its next is null, right? So if I did heads next here, so I am pointing at null here, right? And if I try to, right, so what I was doing here, I did heads next here, right? So currently after this, if I did head next here, so I will be pointing at null, right? So I cannot allocate. So head next here will be null, right? So null's next is nothing, right? So it is basically segmentation fault, right? So for that, and if I would have been removing this, because earlier part I was just doing head is equal to head one, right? This was the mistake I was doing. So after doing head next here, right? If I did head is equal to head next here, then I'll be pointing to null, right? I'll be pointing to null here, but I cannot allocate anything to null, right? So this would be causing the error. So that's why I just removed that line which was doing head is equal to head next, and in here I just pointed head next here, and the code started working. Because now what happens when I did the changes, that my first node was 2 here, and after that my head one pointer was here, and I saw that yeah, 3 is less than 5, so my head's next pointer will now point to 3, right? So my head is here, so my head's next now will be 3, right? So this is how, because if I did head is equal to head next too early, then I'll be standing at null, right? So this is my head, I'll be standing at null. So that means null means nothing, right? End of the linked list. So I cannot add anything to null, right? If I'm standing here at head, then I can add something, right? So this was the common mistake I was committing. And in the last, this was a silly mistake I was committing here in the last part also, right? So if my linked list is getting empty, right? So let us say that if my linked list was getting, suppose both of these linked lists were like this, and this was my linked list, right? So if this linked list is getting over because its size is smaller than this above one, right? So if my this linked list is getting over and both of these nodes are added, right? So I am again pointing to heads next here, right? So if I did head is equal to head next, then I'm again pointing here null, right? So I cannot add anything now here. So that's why what I did is I just put heads next is equal to null instead of moving to the null, right? So that was a mistake. So if I submit that, now this code will work, right? So guys, this was the common mistake we can make, or the silly mistake we can make, although knowing the logic or approaches, because we are dealing with the next pointers, and as we can see that dealing with pointers is a bit of tricky thing, and we can commit silly mistake. Although if we know the logic also, then we can make some silly mistakes, right? So yeah, everything else was fine. All the logic, all the algorithm I explained to you was fine, but I just did some silly mistake here in just manipulating the next pointers. So yeah, that was all about today's live stream session. And guys, stay tuned for more such recently asked interviews question, and to stay connected with the Geeks for Geeks practice channel to get such more informative videos on the recently asked interview questions. So happy coding, guys. Bye bye.